Hello everyone. Uh, Welcome to this fifth lecture of Engineering Mechanics series, in which we will be discussing about equilibrium of rigid bodies. Now, this equilibrium is a bit different from the equilibrium that we have discussed in lecture two. In lecture two, we have discussed about force equilibrium. However, in this part of this lecture, we'll be discussing about the force equilibrium as well as the couple moment equilibrium. So the body will be tested in all the conditions of equilibrium, all the forces equilibrium and the moment equilibrium. So for a rigid body to remain in equilibrium, the external forces and moments acting on the body should balance the external forces. In the usual sense, for a statics condition, sum of all the forces acting on the body must be equal to 0, and also sum of all the moments acting on the body must also be equal to 0. So these two conditions must be satisfied by any three-dimensional rigid body for a body to be in statics condition, that the sum of all the forces acting on the body should be equal to 0, and the sum of all the moments acting on the body. And remember that the moments that are generated are the result of these forces only. Moments that are generated are the results of these forces or the components of these forces. So the inclusion of the moments actually happens due to these forces only. And the important thing that we have discussed last time, that why does a moment originates when there is a body and there is some force acting on the body, then there is simply a force acting on the body. Why does a moment, or how does a moment originates? So the moment usually originates when there is a some restriction or constraint on the body, and we'll be discussing about the restriction or constraint in this lecture. Different types of restrictions, different types of constraint we'll be discussing. So in this lecture we will be discussing that. Further, uh, we will be seeing that since these single equation of force can be extended component wise, so we'll be getting three component equations along the x, y and z directions, and further the moments can also be expressed in three directions. Okay, and remember that these moments will be in rotatory form along the x, along the y and along the z direction. So along the x, with respect to this axis, the moment will be in the rotary component, as a rotary component, because the moment is perpendicular to the particular plane acting on it. Okay, now you know all these things. Further, let's try to see one kind of a free body diagram. Like for example, in this crane, we have a load from the top. This load is being hanged. This is the weight of the load, and this is the fixed part. Okay, so this crane is fixed at point A. So the moment it is, we said that it is fixed, that means that it is not allowed to move in the x direction, and it is also not allowed to move in the y direction, because this is fixed. So there is no this movement, vertical movement, no horizontal movement. So these two movements are restricted due to the fixed constraint here. However, on B we have a translatory constraint. That means this cannot go beyond this. So the x movement is restricted and the y movement is allowed. Okay. So along the y, this roller can roll along the y. This roller can roll along the y. So since this is fixed at A, that means the x component is restricted. So when something is restricted, we have an equivalent and opposite reaction due to the Newton's third law of motion. So there will be one reaction coming at this, and similarly the y-axis is also constrained, so there will be one reaction coming to it, like this. This reaction came since the movement along the x is fixed, and also this reaction came along the y because the movement along the y is also fixed, because the point A is constrained, fully constrained. Similarly, the point B is allowed to move in the vertical direction. So there is no vertical component because the movement is allowed. However, the horizontal movement is not allowed, so the component or the reaction B exists. In a similar way as a weight of the body, this body, this crane will be having its own weight also. So this will be hanging along the center of gravity. So usually bodies have CG at the center or at some location outside the center. If the bodies are symmetric in nature, now since this crane is not very much symmetric, so it has its center of gravity shifted towards this side. However, if it would have been symmetric, then it would be at the center. And the reaction from this weight is 23.3 kilonewtons. So as you have seen, what we have done, we have broken down the initial problem in terms of its free body diagram. So the free body diagram represents all the reactions, forces, any gravitational forces, any weight forces, all these things are represented by a free body diagram. Okay. Um, let's see some of the reactions or support connection that may exist. Like in this case, these are the roller contact or this kind of a contact you have seen. Like for example, a car which is having a tire on the ground. So the ground will exert a force with as a reaction. So ground will exert a force on the reaction, and since the horizontal movement, tire can move along the x in both these axes. Along the x, the tire can move. So there is no reaction. However, since the tire cannot go down, so there will be Newton's third law of motion. We will be having one reaction force. Similarly, in this case also. However, in this case, this is a short link. Two links are joined together, and these two links are pinned at this location. So once there will be a movement, there will be, since they are pinned together, so there will be a reaction coming from this. So this body will offer a reaction on this, like this, as a short cable also be an example of this. In a similar way, we may have a collar of frictionless rod. This is a very usual example of a connecting rod on a piston. Piston connection rod is usually seen inside the cylinders of engine, car engine or motorcycle engines, all these things. This is a collar of a frictionless rod. So a reaction force can be offered. Since as you can see, the y movement or this direction movement is not allowed, however the x movement is allowed. Okay, so let's move forward. This is another case. This is a frictionless pin or hinge, like this. So in this case, this can be translated, or this can move in this cannot move in this direction because there will be some load over acting over from this. There is no rollers, so there will be a offered, it will offer the this kind of a reaction also, and the downward reaction also, horizontal, vertical, both these reactions will be offered. So the moment you see these are only some of the examples from the usual applications. However, as you can see the problem, you can see its movement along that particular range, and you can put a reaction force if the movement in that range is restricted. If the movement is restricted, put a reaction force to it. If the movement in the other axis is also restricted, put the reaction force in that also. If the movement in the third axis is also restricted, then you can have to put the movement in that axis also. It's very simple. Like for example, this is a fixed support. Now here comes one important thing. As this is kind of a fixed support, we'll be having the force components also along the x restricted, so X reaction. Y is also restricted, Y reaction. And since once I'll put the load, this will also create a moment. This will create a force couple moment. So due to that, we actually have to put the moment sign here also. We have to find the moments in this case. So remember, whenever there is a fixed support, so this may experience any kind of force. So this is one something very common to you. You have seen the poles, the electricity poles alongside the roads. They are fixed in the ground. So you have seen that there are wires going from one side to another side, and these wires actually produces moments because this is a tension wire. So there will be a force component here, and due to this force component and this length, this will create a moment of this kind at this point. Okay, so whenever there is a fixed support, may exist moment may exist due to the action of the force. Now the force on this column is like this. Okay, there will be no moment because the line of action of the force is same to the fixed point. So there will be no distance. R is 0, moment will be 0. Okay, but if there is some distance like this or this, so then we have to calculate the moment. So whenever there is a fixed point, fixed support, we will offer a moment, force couple moment also. Okay, in this case, this is some kind of a truss shown to you. Trusses are mostly the example used in the civil engineering, and trusses actually used to carry very heavy loads, and you can find these trusses in the bridges or highways. All these things, you might have seen highways or pulls from one point to another. They all carry these trusses because these are the different members of the trusses, and they can take very high amount of loads. So they also may be fixed at one location and may be allowed to rotate, or sorry, allowed to move along the other location. Usually this kind of restriction is done. You will be asking, very surprised to know that some horizontal movement is actually beneficial in some temperature conditions. When the bridges goes under different different changing temperatures, then they may contract or shrink. They may contract or they may expand, and due to which there should be some horizontal movement allowed to accommodate these changes. So always we, at one point we may offer a fixed conditions so that it provides a rigidity to the structure, and at one point we used to provide some displacement, offering of some displacement, and we may also curtail it here so that the displacement should not go beyond certain range. So nevertheless, what should be the reactions at these? So reaction will be only vertical reaction. This is curtailed, this is allowed, so only B is there. At A, both are curtailed, so both are curtailed, so both these reactions you can see. And these are the component forces. P, Q, S will be having horizontal, vertical components. Remember, if there is any force inclined, so inclined force will be having a horizontal component, vertical component. A, a perpendicular or a horizontal force is itself a component in a perpendicular direction or a horizontal direction. Okay. So to maintain the equilibrium of the system, it's important that these forces and moment component should be equal to 0. Okay. And these are the simple equation of equilibrium in a two-dimension case. So there is no three-dimension. So summation of all the forces along x along y should be equal to 0. And since A is the fixed support, so as I said, fixed support will be offering a movement. due to the action of these forces. So the moment equation should also be equal to 0 to obtain the structure in static equilibrium. Okay, so if you have three equations, it can be only solved for three unknowns. Remember that. So you can solve these three equations for three unknowns only. Further, uh, these three equations can be further augmented with these additional moment equations. That means summation of all the moments along A should be also equal to 0 and along B should be also equal to 0. They can be further augmented if required only. So we will see how to implement them in the problems. So these are some of the structures. As you can see, these are indeterminate reactions. That means both are completely fixed at these two locations. The statically determined reactions offered here. So there here actually occurs more unknowns than the number of equations. Okay, there may be another condition in which fewer unknown in the equations are there. So this is actually partially constrained situation in which the horizontal movement in both these conditions are allowed. So this becomes a partially constrained formulation. Another case, these are the three. Here the equal number of unknowns in equations but improperly constrained. So you have this situation also, this situation also. We will see these situations in the coming up examples. So we'll take the simple problem, and this is the very simple problem of a crane that we have discussed, and we have to determine the components of the reaction at A and B. So components: horizontal component at A, vertical component at A, and horizontal component at B. So these, first of all, we'll create a rigid body diagram. This we have already done earlier. These are the components that are required: 1, 2, and 3. So what needs to be done in such situation? We will find out the summation of all the forces equal to 0 and summation of all the moments equal to 0. So summation of all the forces along the x direction, okay, and along the y direction. So let's first of all find the moment. So moment will be find it out at A, because A is the completely fixed location. This will be offering a two-dimensional moment also, because this is completely constrained. So summation of all the moments about A. So which are the forces that will produce the moment? B. This is one force, this is one force, this is one force. These two are at location A also, so R is 0 for them, they will be 0. So B times this distance 1.5. Remember that this B is trying to rotate this body in a anti-clockwise direction around A. So this is positive. 9.8, the usual center of gravity. From this, the distance is 2. This is trying to rotate the body in a clockwise around A. So negative. Usually clockwise we have assumed to be negative and anti-clockwise positive. This also is trying to produce a clockwise. This is negative. So B comes out to be this much. Very simple. We have taken summation of all the moments. Now easily we will take the summation of all the forces. Remember that there are no typically forces. There are x forces and y forces. First of all, take the x forces and y forces we have. B we have already obtained. So we need two equations. Summation of all the forces along x and along y. We will be having two equations, two unknowns, determined solution. We'll find it out. As you can see here, we have added all the x component in the x equation, all the y component in the y equation, and obtained the reactions very simply. Okay, this is another problem, and this is a loading car which is at rest on an inclined track, and this is one cable that is pulling it. This is pulling it or doing it something, but whatever it is, this is offering a reaction to it. Sorry, this is offering a tension to it. This is a cable, na? So we will put the tension. Now horizontal movements are allowed on these wheels, so there will be this kind of reactions will be obtained. First of all, just try to make a free body diagram. This G will be offering this direction force. So this will be having. Remember that the x and y axis should be along the problem. So this problem is inclined, and let's just choose this point. You can take this as your x-axis and this as your y-axis. Sorry, this as your x-axis and this as your y-axis. So we have shifted or turned our y-axis according to our problem. So this is G along this direction. So G will be having a component along x and along y. How they will look like? Just see how the component will look like. So this is a tension which is along this. There will be two reactions offered, and the G will be having the mass is shown, I think, known. So this is 5500 lb. That means 5500 pounds. So this 5500 pounds will be having a vertical component and horizontal, or you can say a component along the x or along the y. So what needs to be found in this problem? Tension in the cable and the reaction at the pair of wheels. That means we need to find these two reactions and this tension. Okay, so remember that we have to include the moment equation, because the force balance, this is a 2D problem, so we have two equations in the force balance, x equation and y equation. Summation of all the forces along x, summation of all the forces along y. So these two equations can only give us two unknowns. So we need to include the moment equations. So what needs to be done? First of all, let's say this is a particular point A. We have taken x and y, and at this point, let's say we'll be having, let's say this point is at A, and let's try to take a moment along this point. Okay, so this is along A, to T and R1 both will be nullified because they will be along this A only, so no radius, 0. So try to take the moment from R2 times 25 plus 25, 50, and their components, this is 6, so 4980 times 6 plus 2320 times 25, and you can find it out these two components like this. Okay, by using simple trigonometry, find out these two components, time this, so you can get the R2 from here. Simply write this, and while using a moment calculation, always remember that whenever you are doing a moment calculation, these forces actually, like for example 4980 times 6, this is in negative. Why? Because just try to put this point, this force is trying to rotate this body in a clockwise way from A. So if you, from A, this G is trying, this force is trying to rotate the body in a clockwise. We have seen that we have taken or assumed clockwise rotations as negative. In this case also same. However, in R2 is trying to rotate the body in a anti-clockwise fashion. In a similar way, you can find out reactions at B also. So you'll find the R1 in this case. Just simply find the reactions, simply find all the component of the moment offered by the reactions, and you'll be getting R1. So R1, R2 is obtained. Now we'll be requiring T. So T can be obtained through force balance equation. So force balance equation is simple. Try to balance the forces along the x direction. So T is in the minus direction and 4980 is in the positive. This comes out to be T. So in this way we have obtained the balancing of the bodies. So we have, using the force balance, moment balance, we have ensured that the bodies are in static equilibrium, and through these equations we were able to obtain the unknowns. Another sample problem where a frame support of the roof of a building is given. The tension in the building cable is somewhere 150 kilonewtons. So this is 150 kilonewtons. Okay, determine the reaction at the fixed end E. So this is the fixed end they are seeing, and this type of support we have already seen. No horizontal movement, no vertical movement, and there is movement also. Okay, so first of all, try to make a free body diagram of this. So the free body diagram we'll try to make. This becomes a free body diagram. No horizontal movement, so a reaction force will come, reaction moment will come, and this is along this force is given, I think 150 kilonewtons. So now we'll use a moment equation and moment balance and force balance. So moment balance and force balance we'll be using. First of all, we'll use the force balance. Now remember that what we need to find out, we need to find out these three equations, 1, 2, 3. So to obtain these three equations, first of all, we'll find the force balance in the all the x components. So this is one component Ex, the another component will be the component of this. Try to find out the component of this in this direction. This will be cos theta. The component this on this horizontal will be cos theta. That means base upon hypotenuse 4.5 by hypotenuse 7.5. Hypotenuse of this can be obtained by Pythagoras theorem. Okay, times 150. So this is E minus 19 came. Okay, Ex came. Now for the other things, other Y, we will find out the force balance of Y, and similarly Y can be find out as a force balance. This vertical component of this Ey, and all these they are along this, so no, they will be added. Okay, 1 2 3 4, 20 times 4, they will be added negative because they are in this downward direction. Ey comes out to be like this. Now the moment balance. So moment balance is very simple because we have to find out the moment from the point E. This is the fixed support. So from this we have to find out the moment. So we'll take these 20 times 7.2. So moment of this times this distance, moment of this times this distance, this times this times this. All the force happens, and then force, which component will be there? Active, this component. Okay, this is vertical component. Okay, this times this. Actually, this is the vertical component. This should be there. Yes, times and the moment itself, ME. Solve this for ME and you'll be able to obtain the ME. So remember that the important thing in this problem and all such problems will be to effectively and purely calculate the force balance and moment balance for you. Okay. Um, we'll talk about equilibrium of a rigid body in 3 dimensions. So in 3 dimensions, nothing fancy happens. Only the third dimensions actually gets added, and you also have to actually two more equations also increased. So now you have total of 6 scalar equations. So you can get 6 unknowns from here. Okay, expect the condition for equilibrium of rigid body. This is for a 3 dimensional case, and further these equations can be solved for maximum of 6 unknowns at the reaction supports or at the components. So just remember that these things will be there, and there will be, as there will be a 2D supports will be there, so in that case 3D supports will be there, and you can go through them very easily. The logic behind these supports, everything remains same. Okay, the logic and these things will remain same on these 3 dimensional structures also. Like for example, this ruler, even if you produce a ruler, all this force component, this is allowed, only this is not allowed, so there will be only one force component. Okay, in case of a wheel on a rail, this is the situation for a train, a typical train wheel. So only the movement along this x direction is allowed. The rest two directions are curtailed. So this is required. In this is a ball socket condition, like you have seen in a remote control. This is a typical ball and socket condition. This is also seen in gears of the car. In car gears, you have also seen the ball and socket. Here, all the three times things are constrained in x, y, and z directions. So these are very simple, and you can see it, and you can place your reaction forces accordingly. You can also go through them. They can also produce some moments. Different problems may be having different nature. You go through them, and these are very self-explanatory. We will try to see one problem, a very important problem, and such type of problems will be there in the coming up exams also. These are very important problems actually, and this actually brushes up all the things that we have learned till now. A very important, very good problem actually. A sign of uniform density. This is a signboard. This is something, a signboard. You have seen these signboards, advertisement boards, which is fixed somewhere. Fancy people are there on this advertisement board. Maybe a toothpaste advertisement, or a shoes advertisement, or something else. So they are fixed at one location. They may be tied to the to other some locations through these cables, small strings, so that it will not fall. So this is one part, and these are the dimensions given to it. I would like to know the tensions in the cable and the reaction at A. I would like to know what is the tension in this cable and what will be the reaction tension in this cable, and what is the reaction at A. So as we have seen that we have used in statics, we have used force balance and moment balance. So just look at this problem. As you can see, first step is to first of all to make the free body diagram. Now at location A, this is a three-dimensional problem, fixed support. So we will be offering three reaction forces along the x, y, and z directions. First thing. Another thing, this is this force component here, or tension component, is again lost in space. So you need to find out the unit vector for this. Okay, brush up your chapter lecture 2 and lecture 3. So in this, or lecture 4, you will be getting how to find out the unit vectors along these two strings, and as you will be getting the unit vectors, you will be able to obtain the forces. So once the forces are obtained, just resolve these forces things along the components. Summation of all the forces equal to 0, summation of all the forces along y equal to 0, z equal to 0, and in a similar way, what will be the moments originating due to these two cable tensions, because there are no other force. All the three reactions here, these will be the three reactions, and these are the two forces. Only these will be there in the picture. So let's see the free body diagram first. This is a typical free body diagram. So one is okay, the weight of the plate itself, which is minus 270 in the j direction. So I'll write everything in vector form. Minus because this is along against the y direction. As I said, there will be three components along the x, y, z directions. I, ax, I. In vector form, I'm writing all these things. Remember, when there is a 3D problem, try to write everything in the vector form. I, j, k. So you'll be able to solve these problems much easily. And there's a tension TBD, BD, and TEC. So I've created a free body diagram. Now we have to find these forces, TEC and Whenever I said we have to find the tensions, remember that we need to find the magnitude of the tension. We do not need requiring a vector. Vector is a mathematical term. We require a magnitude. So we require a magnitude of this tension. We require a magnitude of this tension. We do not need a direction. It's immaterial at this location because this is lost in space. Okay. So we will talk about vector form. So what we'll do, as I said, we'll first of all obtain the unit vector along these two axes. And I have already told you how to obtain the unit vector. So vector TBD will be vector along this. This will be magnitude of TBD. This is magnitude of TBD. What needs to be find times a unit vector. This is a unit vector. RD minus RB. RD minus RB. So RD is this, RB is this. How you'll find out RD minus RB? You have to go from B to D. As a unit vector, you have to go from B to D. So by going from B to D, you have to travel minus 8. This is 6 plus 2 minus 8. So this is minus 8 times I. Then plus 4 along the this plus 4. This is 4 feet plus 4. And then this is J along this direction. So against this minus 8 becomes a unit vector divided by square root of 8 square, 4 square, 8 square. This becomes 12. So we'll be having magnitude times a unit vector. This gives you a vector TBD. In a similar way, we'll be obtaining vector TEC, vector along this. Once you have obtained these two vectors, it is very easy to do the rest of the calculation. How will you do it? You have to find the force balance and moment balance. Now you know all the vectors along x, y, z. Along x, y, z. The vector TEC along x, y, z is there. X, y, z is there. So you only need to find out. You only need to put the force balance and moment balance. How will you do this? This is the force balance. So sum up all the forces along the x direction. This is x. Okay. And the x component of TEC. Pick up this x component of TEC. This one. TEC, this one, sorry. Okay. And then put the x component of TBD. TBD, x component, put it I component from here. In a similar way, AY, J component of all the three forces. And J component will also include the W, the weight force. Then in terms of K, put or obtain all the Z forces. The Z component of these two tension forces and reaction in Z. They will provide you three equations. 1, 2, 3. Then we may be having a moment equation at location A, because this will be offering a moment also. And since this is a three-dimensional problem, so moment will be having three components. Okay, so what will be the forces that will produce a moment? So moment, remember, will be produced along I, J and K. Moment summation of all the forces along I, J, K. So try to take the moment of these forces along this. So TBD will produce a moment along this at A. So TBD times the position vector RB. RB position vector is already obtained. Okay. And then RE position vector. RE will go from here to here. Okay. So this will be RE times TEC. TEC is the, remember, this is only the X component. And then 4 FT times I times this. Okay, this is W. This will all produce the moment. And why 4 FT? Because this is this distance, 4 distance from this 4 feet. So W from A will be like this moment. try to take the moment. RE times 4EC, RB times TBD, and these are the active forces times their distances. Now put all the J and K components. I think I will not be there. I of these components will not be there, so there will be J components and K components. During the calculation, we will be getting it. And so we'll be getting all these 5 equations. So we have 5 equations and we have 5 unknowns. What are the unknowns we have? TBD, TEC, and AX, AY, and AZ. 5 unknowns. So we have 5 equations, 5 unknowns, we can solve it. The best way to do these problems is to do it by hand calculations and do it by 2 or 3 times. And the more you do these problems of unit vector and all these things, of these 3-dimensional problems, you will become more comfortable in solving such problems. Okay, so this will be the end of it. We'll meet you in the next lecture.